So this is our very first lesson of new material for advanced functions. And it's section 1.3, properties of graphs of functions. You already know a lot of properties from grade 11, and we're going to build on those now. So when we read functions, you know this already, we read from left to right, and that means from negative infinity to positive infinity. We follow the x-axis or the domain. So if I was reading this parabola, I would start at -4 and I'd be reading across this way and going from left to right. So, you know, why is that important? Because if we want to talk about parent functions that are increasing and decreasing. These are all of the parent functions from grade 9. This one's 9, this one is 10, and then everything else is 11. So increasing. Increasing means from left to right, it's always going up. So one of those is this graph right here, y equals x. Going from left to right, it is always going up, it is never coming down. So this is an increasing function. There is another one, the question says there's two. There is another one that is always increasing, and I'll give you a second to take a look for it. The other one that is always increasing is the exponential, because it starts off really low, close to the x-axis, but it's always going up, increasing, increasing, increasing. So those are the two functions that are always increasing. Are there any that are always decreasing? So always decreasing. That means the whole time, like these ones, they're always increasing. Are there any that are always decreasing? The correct answer to this is none. Now you might have been thinking this one is decreasing because it starts off here, it's coming down, coming down, coming down, coming down, but then it has a jump here, right? We have an asymptote right here, so the reciprocal function kind of jumps and then it does continue to decrease. It's not always decreasing because it doesn't actually exist along the y-axis. So we'll talk a bit about this more in the next slide. So here are our parent functions again from previous years. The turning points or critical points, that's what tells you switches from increasing to decreasing. So for example, the critical point on x squared, the turning point is 0, 0. It's also the vertex. It's the same concept. So the vertex is the turning point. That means the function, so starting on the leftmost side of the function, on the leftmost side, it's coming down, it's decreasing. And then it turns at 0, and then it starts increasing when x is 1, when x is 2, when x is 3, it's increasing, increasing, increasing. So turning point is not increasing nor decreasing. A turning point itself is separate from the increasing and decreasing. It actually doesn't have a rate of change, but we'll talk about that later. So the critical point or the turning point of x squared is 0, 0. Which parent functions have intervals of increase? So the y values are getting larger as we read across the domain only from x equals 0 to infinity. So what this means is if I look at any of these pictures and I start looking when x equals 0 right here, 0, 1, 2, 3, 4, 5. So reading to the right, which functions are only increasing when x is starting at 0 going in this direction? So this is what I'm looking at right now. This function, the exponential function, is increasing, but it's also increasing over here. The question that I've asked here is specifically saying which ones only increase from when x is 0 onwards. So a good example is right here beside it. The radical function, it's only increasing from when x equals 0 to infinity. So from when x equals 0 all the way to infinity, the square root function is increasing. It has an interval of increase, meaning it's not increasing the whole time. It's an interval, it's a part. It's increasing from 0 to infinity. It's not always increasing, like what we talked about on the previous slide. This exponential is always increasing. This one just has an interval of increase here. So it says there's 3 of them, all right? We've got one of them. This one is increasing from x equals 0 until x equals infinity. Can you identify the other 2? One of them is here. Our parabola, quadratic function, when we've got our turning point, it's increasing from 0 on. right? On the other side, it's decreasing, but there's an interval of increase right here. So y equals x squared, or g at x equals x squared, it also has this same property. It has an interval of increase from 0 to infinity. And there's one more. It's the absolute value function. So it's decreasing here, but at 0, the function starts increasing. So we don't really talk about the y values with increase and decrease. We just talk about the x value. So it's increasing from when x is 0 until x is infinity, way, way over here. So those are the three that increase from 0 to infinity. There's one function that has no intervals of increase, and we already talked about this one. This is the reciprocal function. This one is decreasing from negative infinity to 0, but then actually at 0, it's neither increasing nor decreasing. It doesn't exist because of the asymptotes. So we kind of hop over and then we go just to the right of 0, like 0.00001, and then it's decreasing here. So it has no intervals of increase. It's decreasing on all its intervals. This one only has intervals of decrease. Which three functions have intervals of decrease over this domain? So what this means is, this is a better way of writing this kind of thing here. Up here I wanted to say from when x is 0 to infinity. But to write that with proper notation, when we're talking about intervals, to write that in proper notation, what I should be writing is, if we were back in grade 11, we would write that as x is greater than 0. Not greater than or equal to 0, or greater than 0, from when x equals 0 to infinity. But we have a different way of writing that now. The way we write this now, instead of saying when x is greater than 0, we write it kind of like a coordinate. We say starting at 0, ending at, in this case, infinity. So these two are equivalent to each other. We're going to use a lot of that new notation this year. We'll talk more about it. So here it is, this notation. I want to find, sorry, that was my phone. So this notation here is saying I want to start at negative infinity, which means way off to the left of a function, and go all the way to 0 and stop there. So this is like my left hand side, and this is my right hand side if I'm reading from left to right. So which three functions are decreasing from negative infinity all the way to 0? So our parabola is one of them, right? Here are x values. Our x values of negative infinity all the way to 0. The graph at negative infinity would be way up off the screen, way off in the top left-hand corner, decreasing, 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 and then it turns, so it doesn't increase anymore. So this one, so you can write this down on your paper, for which three functions have intervals of decrease for this interval here, this domain, y equals x, g at x equals x squared is one of them. And this, we used to write it as x is less than 0, but we're going to use both notations now. So what's another one? Another one of the three functions that's decreasing all the way to 0. So from the left to the 0, give you a second to look at them. There's two more. This is one of them. This is decreasing, 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 decreasing all the way to 0. And we're not including the 0. Remember, this 0 isn't included. It's a turning point. It's not actually increasing or decreasing at a turning point. An asymptote as well is not increasing or decreasing. So that reciprocal function is decreasing over this, and every time x is less than 0, our function is decreasing, but we write that like this now. And there's one more. This is the last one here. Decreasing, decreasing, decreasing all the way to 0. So those have intervals of decrease from negative infinity to 0. Now these brackets, we'll talk more about them later, but if it's a round curved bracket like what you see here, that means we're not including. So we're not including 0. It's not including 0 because 0 is a turning point. If I had a square bracket, then that would mean I'm including 0. But 0 is a turning point, so it's not decreasing, so it's a round bracket. And that's just a minor point, but we'll talk more later about that. Now there's one function that has several intervals of increase and several intervals of decrease. Which one is that? It should be pretty obvious. It goes up, it comes down, it goes up, it comes down. That's sine. Y equals sine x. it has several intervals of increase and several intervals of decrease. So if I just, oops, right here, so this is increasing, increasing, increasing. I just kind of highlighted that, and the other parts from the max or a min. As soon as we get to a max or min, then we start going from increasing to decreasing. So the question says, explain what are the turning points. So the turning points are all of the maxes and mins. Every max or every min is a turning point or a critical point. Functions can be described using increasing and decreasing intervals. So we just talked about that. That's just what that first sentence is saying. So another big property, that's today's topic, right? Another big property is characterizing them with points of continuity and discontinuity. So we've already gone over this property, continuity and discontinuity. These are probably the easiest characteristics we're going to talk about today. Any function is continuous if there's no holes in it or breaks in it. It just goes smoothly. You would not have to pick up your pen. You could keep drawing, 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 drawing. That's continuous. Discontinuous is like this. You have to pick up your pen to get from one spot to another spot. There's an asymptote or there's a hole. There's something going on. There's a break in the graph. And that's the point of discontinuity. This is the tangent function, which we didn't really talk about last year in terms of what its graph looked like. We will this year though. So the tangent function, or the red parts are the graph itself, the green are asymptotes. The graph of the tangent function is discontinuous all over the place, right? It's this one here, 90 degrees, it's discontinuous when x is 90. It's discontinuous when x is 270. It's discontinuous when x is negative 90. So that's why I put plus or minus 90 there. Plus or minus. It's discontinuous all over the place. It continues on like this to infinity. So we have to go back to grade 11 and use this formula. If you forgot it, you need to memorize it again. It was our arithmetic sequence formula. We use it this year whenever we have a repeating pattern like this, because I need to state where all of the points of discontinuity are. Where are all the points of discontinuity here? Well, there's a lot of them, and they occur for infinity. I'm not going to sit here all day and list them all. So I'm going to use this formula that we learned last year for repetitive patterns. So hopefully you remember this formula a little bit. If I wrote this out, so we usually start with the first positive. So our A value, if you remember, in this formula is the first positive one. In this case, we're going to say that's a 90, right? Or this is going to be our A value right here, our first positive. So we've got one at 90. We've got a point of discontinuity at 270. We're going to have another one at 450. So there's a sequence. What is the D? Remember D? D stands for the common difference. What is the common difference between all of these points? It's arithmetic. So it's 180. The D is 180. So I'm going to put this into the formula. My general term formula means this Tn is any point of discontinuity. A value is 90. That's the first number. Now, again, there's no official first number when you're talking about sine, cos, tan, because they go on to infinity to the left and to the right. So there's no actual first value. But as I said, we usually say the first positive one, meaning the first one to come after the y-axis, we use for our A value. N is infinite. N is the number that you have. I have an infinite number of asymptotes. And my common difference is 180 because there's 180 added on between each of these terms, 180 degrees. So we clean that up a little bit. And we're going to distribute that 180 kind of backwards into the n and the negative 1. We get plus 180n minus 180. Collect like terms. We've got some constants here we can put together. So we've got negative 90 plus 180n, or you could write it the other way. So this is a general term. That's what this is called. This is a general term for all of the asymptotes. So if I asked you, what is the location of the 10th asymptote? You would sub in a 10 for n, and you would tell me where the 10th asymptote is. The back of the book sometimes takes this answer and writes it in a factored form. For me, on a test or quiz, you don't need to go any further. You don't need to, so they might factor the 90, for example, or negative 90. I don't know if they might take it a positive or a negative 90. That would leave you with a negative 1 plus 2n. You might see that in the back of the book. You don't need to factor them out. The back of the book also sometimes uses for its a value, it uses the first negative one, which is just harder because then your a value is always negative. So when you look in the back of the book, if you don't have the same answer they do, it could be they started with a different a value, but as long as you're subbing into the formula properly. We do this anytime, usually only occurs for us with sinusoidal functions, anytime you have to show like an infinite number of something. In this case, it's asymptotes. It could be infinite number of maxes and mins. It could be infinite number of turning points, critical points, infinite number of intercepts. Whenever you have sine, cos, or tan, and you have a repeating function, and you have to state for me a characteristic of it, such as where are all the points of discontinuity, something that occurs over and over again, then you need to use this formula here. So please memorize if you have forgotten that from last year. The easiest type of symmetry is called even symmetry. So the example of the graph I've put up here on Desmos has even symmetry. And the reason you know it has even symmetry is if you do horizontal reflection. So if you take any point on this blue function and you reflect it horizontally, moving, you put it across the y-axis, it will land right on top of itself. It's symmetrical. If I folded this down through the y-axis, if I folded this like piece of paper in half, it would be exactly the same. So I'm going to just show you here. I'm going to reflect it horizontally. It's, never mind the stretch, but it's reflecting it. You can't really tell, but that's reflecting it horizontally. It's going from the original one was here, and then it gets flipped around. It's hard to tell. It gets flipped around, it's right back where it was. So that's called even symmetry. When a function, when you flip it horizontally, when you reflect it horizontally, it lands right back. This graph I've drawn has symmetry. So it's symmetric about the origin. Imagine taking this graph I put on Desmos and flipping it upside down, flipping it vertically. If there were an a value, a negative a value, it would look like the blue one, right, with a negative a value. So this is the original function here, and this is a negative a value. It would flip it upside down. So the reason I'm saying this has symmetry is because if you go back and imagine the original, but imagine now flipping it horizontally, sideways, reflecting it sideways, putting one point on the other side of the y-axis and doing that with all the points, we would also have some symmetry there. So let me show you that here. Here's a horizontal reflection. It's stretched there, which ignore that, but that's the horizontal reflection. So flipping it side to side, flipping it horizontally, reflecting it horizontally, looks the same as reflecting it vertically. When you have that happen with a function, whether you flip it vertically or horizontally, and those two are going to land in the same spot. So there's a vertical reflection, there's a horizontal reflection, they both are exactly the same. You have what's called odd symmetry. So here's some more information on symmetry. Functions can be described using symmetry. There's odd, even, which we just talked about, and neither. Neither is obviously, neither of the other symmetry works. Symmetry can be determined graphically or algebraically. Graphically, let's start with the bottom one here, the even function. The Even function is the one that, it's the parabola is the basic even function, right? Here's the parabola. When you flip it sideways, when you do a horizontal reflection, it lands right on top of itself. So an even function that is symmetric about the y-axis. So the y-axis is your point of symmetry. Algebraically, we're going to talk about this next. The odd function, an odd function is the one that has two reflections. You have if you reflected this one horizontally, or if you reflected it vertically, it would land in the same spot. Another way to think of that is if I took this first and reflected it horizontally, and then I took that new image and reflected it vertically, I would land back here again. So that's the symmetry for an odd function. Classify each of the above parent functions as even, odd, or neither. So let's start with the first one, the line from grade 9. Well, what do you think? Even, odd, or neither? Take a guess. I will tell you it is odd. It is odd because if I reflected it horizontally, it would kind of go like this. And then if I went back and reflected it vertically, it would be the same thing. So that's odd. The parabola is even. It's the main one you want to keep in your mind all the time. When you think of even symmetry, always think of the parabola. That's symmetric about the y-axis. So that's when you fold in half and it lands right on top of itself. If the fold line has to be the y-axis. So what about the reciprocal function? What do you think? Even, odd, or neither? It's odd. It's odd because if I took the top quadrant, the top right quadrant, and I flipped it horizontally, I took this piece here and I flipped it over here, that would be and I took this side here and I flipped it over here, that would be the same as if I reflected it the other way vertically. Absolute value. Absolute value behaves in a lot of ways like a parabola. It has the same kind of turning point, the increasing, decreasing characteristics are the same, and the symmetry is the same. This one is also even. What about the radical, the square root function, the radical function? What do you think? See, if I flipped it horizontally, it would be here, but if I flipped it vertically, it would be down here. So it's not odd because those aren't the same. And if I flipped it horizontally along the y-axis again here, it's not where it was like the parabola would be. So this is neither. And then the exponential function. So we want to always start, when you're visualizing these, you always want to start first with the horizontal reflection, because if the horizontal works, then it's going to be even like the parabola. That's the one you want to rule out first. So if I reflected horizontally first, it would be like this, right? So it's not even because it didn't land on top of itself. So it's not even. So now I think of the vertical reflection. The vertical reflection would be down here, and it's not where the horizontal reflection was. So this one is also neither. And then the last one is sine. So again, we want to start with looking for even first. Even means any point that's here, when I reflect it, is going to be over here. So if I did that, my horizontal reflection is going to look like this. It's hard to see. That's not the same. So it's not even. Now, if I think of going back to my original sine wave and flipping it down, so if I took this point here and moved it down, we're talking about a vertical reflection now, this would go right where this one was. So this one, the horizontal flip is equal to the vertical flip. So this one is odd. Sine wave has odd symmetry. For each function, so now we're going to solve this algebraically. So determine f at negative x and negative f at x. If I just go, if I circle over here for you, we're going to always look for even symmetry first. It's an easier one. So even symmetry means, a horizontal flip means wherever there was an x, so let's say this one had an x value of, let's say that's a 3 there. that x value of 3 is in exactly the same spot when I make it a negative 3. So I'm taking all of my x values and I'm switching them around to get a horizontal reflection. I'm moving it horizontally. So all my x values need to have a negative. So what that means is here, the first thing I'm going to do is take my, I want to find f at negative x. F at negative x is going to equal, so everywhere, remember back to grade 11, if it was f at 2, we would put a 2 in for all of those x's. But in this case, I'm going to put a negative x in for all of those x's. So I'm substituting in a negative x. That gives me f at negative x gives me 3. So negative x cubed, that's negative x times negative x times negative x. That's going to be a negative x. So I'm just going to put the negative here and put my x here. So that's negative x cubed, that. And now negative 2 times negative x is going to give me a positive 2x. So is this new equation equal to my original equation? Are these two equal to each other? If they are, then we have even symmetry because they should be equal. They're not, right? The signs have changed, so it's not even. F at negative x does not equal f at x, so it's not even. So now we're going to check to see if it's odd. So odd symmetry algebraically has this property. Now we already found this equation right here. Right? We already found f at negative x right here. So I want to see if that's going to equal this part, negative f at x. So we're looking for negative f at x. Negative f at x. I go up to my original equation and I just put a negative and put a bracket around the whole thing. Whatever I had in here, I rewrite it, but I just stick a negative in front of the whole polynomial. So negative f at x is equal to, distribute the negative in, negative 3x cubed plus 2x. So does negative f at x, that's the vertical reflection, that's flipping it all down, does it equal f at negative x? Are these two equal to each other? If they are, it will be odd. And they are equal to each other. So that function has odd symmetry. Right, therefore, we've got odd symmetry because those equations are the same as each other. Let's try again. So if you want now, you can pause it, try and do it yourself, and then start playing when you're ready to catch up. So I'm going to start by looking for the even to see if it's an even function first. If it's an even function, remember, if it's even, then my equation that I was given in the question should equal, when I substitute in a negative in for the x's, if it's even. So let's see, f at negative x. So I'm going to put everywhere I had an x, I'm going to substitute it for a negative x, like that. So when I simplify this, I get negative x squared. Negative x times negative x is just positive x squared. So that part's going to turn into a positive. So I still have my negative 4 in the front, x squared plus 1. So take a look at that. Take a look at this f at negative x. Is f at negative x equal to f at x? Are these equal to each other? Yes. So it's even. Therefore, this one is even. Okay, the last property we're going to talk about is end behavior. End behavior. It talks about what's happening at the end of the function. What's happening where the arrows are at the end of your graph. It's often convenient to use a symbol infinity when we use this notation, as x increases to large positive values. So instead of saying when x gets really, really big, x increases to really big numbers, we just write x approaches, that arrow means approaches, infinity. So we use this notation if we want to talk about when x is on the left-hand side of the axis, as x is going really, really far to the left, it's decreasing to getting really large negatives, we would just write as x approaches negative infinity. So this is a better shorthand for writing end behavior. We have a graph, and so there should be arrows here and here, but the program didn't put them in there. So you can put them in, let me put them in too so we can all see them. There should be an arrow here and an arrow here. For the graph shown, state end behavior. So this is our new, if you look ahead to all the other words, you know all the other words, you know all the other characteristics, properties, but end behavior is our new one. So end behavior says what's happening at the end of the graph. What's happening at the end of the graph? Right here, I'm going to highlight, this is one end, right? What's happening at that end of the graph? So at that end, as our x's get bigger and bigger, so right, this is 2.0, 3.0, 4.0, as they get bigger, as our x values approach infinity. As our x values get bigger and bigger, what's happening to the y values? Are the y values getting bigger and bigger, positive, or are they getting negative? So that's this first part of this notation we're doing right here. As x approaches positive infinity, look at the graph, it's getting bigger and bigger. Y, it's getting higher and higher. So y is also getting really big. Y is also approaching positive infinity. Now we have to look at the other end. Here's the other end of the graph down here at the bottom. This end, what's happening at this end? So at this end, as our x values approach negative infinity, that means here we've got -2, -4, -6, and so on. As if our x-axis kept being drawn in this direction and our graph was being drawn and drawn, as our x's get to negative infinity, what's happening to our y values? So as x approaches negative infinity, our y values are approaching also. They're getting lower and lower. They're also approaching negative infinity. So that's what's happening at the end, if there were an end, that's what's happening at the end of this graph. One end is up really high, one end is down really low. So that's all end behaviors. That's the last new characteristic we're talking about today. So let's just recap some of our other ones. Intervals of decrease, intervals of increase and decrease. So let me go to my highlighter here. Intervals of increase, first of all. So we got the turning points are really important when we're identifying increase and decrease. We need to know where the turning points are. So I'm just going to go here, and let's say the coordinate of this turning point is 0, 1. That's what that one looks like. We don't really need the y value, but here we'll say this one is, that looks like maybe 2.3. 2.3 and -4. Again, the y value is not really important. So the intervals of increase. Intervals of increase. I'm going to switch to a highlighter. This is increasing, 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 increasing. That highlighter is not that great. Okay, so this whole part here is increasing. So there's my first interval of increase. It's increasing, and I'm gonna, if I use the old way of writing, I would say it's increasing when x is less than 0, it's increasing. But using our new notation, I'm gonna write it like this, from negative infinity to 0. That's an interval of increase. There's another interval of increase. So the other interval of increase is here. That's an interval of increase. So there's another one, and that's when x is greater than 2.3. the function is increasing, or we write that as from 2.3 to positive infinity. Our function is increasing. All right, what about intervals of decrease? So it's decreasing here. The graph is coming down here. This is an interval of decrease. So writing that the old way, I would say it's decreasing. We always use x values, so it's from low to high. So from x is 0 is less than x, and x is less than 2.3. That's the interval of decrease. But writing it the new way, so we technically, when we write it the new way, we start with an x, saying that we're talking about x values. X is an element of, and we just write 0, 2.3. And we need this piece in front, the x is an element of, otherwise it just looks like a coordinate. So an interval of decrease has to be written, it has to include your independent variable, in this case it's an x, to tell me that this is not a coordinate I'm writing down, this is an interval. Next question is about continuity or discontinuity. So does this graph look continuous or discontinuous? Remember, if it's continuous, it means if you were to draw it, you would not have to pick up your pen. You could just keep drawing it. So it is continuous. And symmetry, so symmetry has to be around the axes, right? It can't just be like if I drew a parabola. We know parabolas have even symmetry, but if I drew a parabola over here, right? Once I reflect this parabola, it's going to be way over here. This no longer has even symmetry because it didn't land back on top of itself. So even though the parabola itself has some symmetry, according to the y-axis, this one doesn't have any symmetry. So looking at the graph we have here, we look for even symmetry first. So if I took this point here, this 2.3, negative 4, and I flipped it over here to negative 2.3, negative 4, it's not landing on top of itself, so I know it's not even. So I can try another point, like say about 4, 4 is about a point somewhere over here. There's another point there. That's not landing back on itself. The only one that is the one that's right on the y-axis. But because it's not landing right back on itself, again, it's not even. So is it odd? If it's odd, it means that if I reflected it the other way, it would land on my other dot. So if I go back to this dot here at 2.3, negative 4, if I reflected that vertically, it would go to 2.3, positive 4. But that's not the same as this one down here, right? These two are not in the same spot, so this one has neither symmetry. Neither even nor odd. Another way to think of odd symmetry is if you have a function, so I'll draw one that is odd, like this is odd. If you have an odd function, and if you think of taking a pin and putting a pin right in the middle, imagine your function is made out of metal. This black curve is made out of metal. And I put some kind of pin through it and I spun it around. If I spun it around, I gave it a push and twisted it around, would it land after a 180-degree spin, would it land on top of itself? Yes, it would in this case. So that's another way to tell odd symmetry, is if it's called rotational symmetry, if you like to envision it that way, instead of two flips. If you could rotate it, if you have to go right through the origin though, you have to imagine that pin being pushed, or you're holding your thumb on it right in the origin, that point's not moving, but the rest of it is spinning around, then that would be another way of talking about odd symmetry. The last one characteristic is turning points. Turning points are any place we change from increasing or decreasing, and we already labeled them there kind of in light blue, so I'll put them up here again. We've got a turning point at 0, 1, and we've got another turning point at roughly 2.3 -4. So those are our 2 turning points. I'm just going to erase this because I think I have more stuff coming up in a second here on my screen. Yeah. Okay. Section 1.3 starts in your textbook on page 17. So this is our first piece of new material for the course. So very important that you don't slack off on these characteristics because we're going to use them for the whole rest of the semester. And all it is new terminology, right? You're not really doing much math at all. In the symmetry, sometimes you are because you're subbing in maybe, but there's very little math going on here. Calculations, I mean. So be sure to read through the part in your textbook that refers to section 1.3. Make extra notes for yourself. There may be something that the textbook has worded it or shown you an example and you say, oh, now I get it. You didn't get it before, but you get it now. Very common in math to not understand something the first time, but the second time the light bulb goes off for sure. So you can watch this video twice or you can go through extra textbook questions, but certainly the second time through will really help you a lot. Then you've got some questions here. So I no longer will tell you specific questions to do. You will choose your own homework questions in grade 12. You will decide what you need to focus on. Maybe you're really good with the symmetry and just need to do a little bit with that, but the end behavior, you're confused. You're going to do a whole bunch of end behavior questions. You're going to decide what you need to do. And if you decide you don't need to do anything, I can almost guarantee you that's the wrong decision. So find some questions to do a little bit of everything. There's a correction for your textbook. And when you get to number 10, you'll just read this here to see. So please pick a good variety of questions to do and ask me questions if you have any. That's it.